Now let's get into temperature and reaction rate. So, some things that we got to realize, things that I think make sense, right? All reactions go faster as our temperature increases. Remember, K, our rate constant, is temperature dependent. So that's the first thing. All reactions go faster as temperature increases. Endothermic reactions are affected to, a greater degree than exothermic. That kind of makes sense too, since endothermics require heat in order for them to go. And so in general, basically a rate will double every 10 degrees Celsius. And it's a general rule, but it's roughly. So those are just some background information, right, that we have a temperature effect. So when we're measuring rate constants or looking at rate expressions, temperature is really, really important, something to remain constant for the particular experiments that we're actually doing. And so we have Arrhenius, who really describes the equation, which basically defines the relationship that we're discussing. It defines how the rate constant changes with temperature. And the Arrhenius equation looks like this, where we have K is equal to A E to the negative EA over RT. So we have some new terms here. We have activation energy. It's something we're going to be talking about a lot now, is this idea of activation energy. We have our R value, which is our thermodynamic R value. Our activation energy, we tend to see in kilojoules per mole, maybe joules per mole, but, we can convert back and forth. And then our temperature has to be in Kelvin due to our R constant. We also have the frequency factor, somewhat of a nebulous term, and then we have our rate constant. And so with some manipulation, we can derive, Arrhenius derived, a linear expression for this. That if we were to take, let's say, the natural log of both sides, we would have the natural log of K is equal to the natural log of our frequency factor plus EA over RT. We should have a negative sign out in front of that. Right, so taking the natural log of both sides breaks this equation down to what we see here. Remember that taking the natural log of E, that's how we go back and forth between those two terms. And so if we rearrange it just a little bit, we end up with our Arrhenius expression. I'm going to write it just a little bit differently here as far as trying to really show the x value here, which is 1 over temperature. And so here we find our linear fit for the Arrhenius. So we have our y is equal to our mx, plus b. So if we were to, look at a plot of this, we would be plotting our natural log of our rate constant versus 1 over temperature. And we'd end up with, something that looks like this. We'd have our y-intercept here to be the natural log of our frequency factor. And then our slope would be equal to negative EA over R. And so it's the slope that allows us to access this idea of our activation energy, since R is a constant. So we can get at that, and we can also get at our frequency factor. So we don't talk too much about the frequency factor. And this is basically, I guess, a way to kind of think about it. It's the number of times that the starting materials basically approach the activation barrier. And that activation barrier that we're talking about is somewhat synonymous with activation energy. So we don't get into too much with the frequency factor, but we do talk a lot about activation energy. And so our activation energy is basically the energy that needs to be surmounted in order for basically the reactants to go over to the products, or to the starting materials to convert them to products. So it's kind of like this hump of energy. The starting materials need to get over. And a kind of a good way to think about it is with, a simple combustion type reaction. If we look at, let's say, the combustion of propane, here being our, balanced reaction for the process. If we're thinking about this in terms of, a barbecue or a propane grill, right? Obviously, we can turn on the gas, turn on the propane. We can, the propane is mixing with oxygen in the atmosphere, but yet there's no fire, right? What do we need, in order to get the fire, right? In order to get the combustion reaction to occur, we need a spark, right? We need some input of energy. And that's the idea of activation energy, is that even though we have molecules that will react with one another, we have to supply enough energy to activate them to react. And then, depending on the reaction, we have smaller or greater activation energies. And so that's how, activation energy essentially works. It's like this hump that we have to get over. So we can represent this in a reaction coordinate diagram, which is a simple plot of the reaction coordinate. And you could think about this as reaction progress. And then we have energy. So if we think about this reaction we have above, the beginning of the reaction, right, we have our starting materials. So we would have our propane, and we would have our oxygen gas. At the end of the reaction, this is a combustion reaction, so we would expect the energies of our products to be lower than our starting materials, right? And so that's the idea of energy being given off, or, exothermic, right? We're starting from higher energy and going to lower energy. But it's not just a diagonal drop, right? We have to have some type of activation for it to go over to products. So this energy here, the energy between our starting materials and the top, is known as our activation energy. Right? This is the spark that we need. And in this case, with propane and oxygen, enough energy is given off once we have some of the starting materials go to product, that now that energy that's given off is enough to supply the activation energy for then more molecules. So that's why the fire doesn't go out, right? That we just spark, we have combustion reaction occurring, the combustion reaction continues to go until we lose, supply, right? Meaning we run out of propane, or, we cover it from oxygen, right? Then the reaction would actually stop. So that's the idea of the reaction coordinate diagram. Just as an aside, catalysts are often used. Sorry, I misspelled that. catalysts are often used in reactions to lower the activation energy. Catalysts do not get used up. They simply facilitate the reaction by this lowering of EA. So if you had, another type of diagram, representing the same energy coordinate, and we could say we're still doing this simple transformation, but just being general here. We would have something like this maybe for the normal reaction. And then we would find that we would have something like this if we used a catalyst. So here we have our one activation energy, and then here would be the original activation energy. So our blue is equal to the normal reaction, while then our pink here is equal to the reaction with the actual catalyst. So we see that the activation energy for the catalyst is much less than the activation energy for the normal reaction. So that's the idea of activation energy, how catalysts affect activation energy. And this idea of activation energy is now really important in going to the next concept. And the next concept we're going to get into is reaction mechanisms and how that relates to activation energy, as well as how it relates to reaction order. Now that we have a good understanding of activation energy, let's go back to the Arrhenius equation, which, remember, is the lateral log of my rate constant is equal to negative EA over R times 1 over temperature plus the natural log of my frequency factor. So remember, this is the linear plot, or the linear fit. There is another form more commonly used, and it's used for solving for activation energy. And remember, we talked about this a little bit earlier, right? This is getting at the slope of the process, right? So when we think about that idea of slope, right, we would have, our delta y divided by our delta x is equal to our slope. So basically, think about it, we could put, two of these really together in terms of a delta. We could say the natural log of K2 minus the natural log of K1, right? There's our delta y is equal to our slope, right? But we're gonna have two of these, right? In terms of the first set minus a second set. So if you look at this, kind of breaks down to the natural log of K2 over K1 is equal to, and if we pull out some common things here, we would have our negative EA over R times 1 over T2 minus 1 over T1, right, plus the natural log of A, and then minus the natural log of A. So we see that that actually drops out of the expression, and we often use this expression or form of the Arrhenius, which is really just a delta form, delta y, delta x form, to just simply solve for our slope. So let's look at an example of using that particular expression. So we got the following data was obtained for the decomposition of dibromo succinic acid in water. What I'd like you to do is we want to calculate the activation energy for this reaction. So here is our reaction. Succinic acid has this kind of backbone in terms of more orgochemistry here. And so we have a hydrogen and a bromine on the central carbon, so that's dibromo succinic acid. And then we're going to react that with water. And phase really isn't that important here. To produce basically a substitution, meaning that we swap these bromine atoms for OH. So we have still the same backbone, but now we have an OH in place of where the Br was on the carbon atom. And then we get two Brs as well. Sorry, this one should have been aqueous. So there's our reaction, and we have the following data. We have our temperature in degrees Celsius, and we have our rate constant, little k. And so if we look at, three different temperatures here, 15, 60, and 101 degrees Celsius, right, we see this increase in our rate constant, like we talked about earlier. Increasing the temperature increases the rate of the reaction. And so that's what we see here. So, this is a clear-cut case, where we're looking at, temperature versus rate constants, right? That's when we want to be thinking about, the Arrhenius. And so we just want to be consistent and pick, two trials to compare. I'll pick 15 and 101. So, the real way to do this is to plot it and get the slope. If we're just kind of doing a quick calculation of the slope or the activation energy, realize that we're just picking two data points. So, if we pick two different data points, the number slightly changes. It should be still pretty close, but would slightly change, right? We would really want to have a number of temperature readings, a number of rate constant results to really nail down the activation energy. But here at least we can approximate it. So I'm going to say, that my K2 is the 3.18 times 10 to the negative second. And then my K1 is 9.67 times 10 to the negative 6. That means my T2 would be, 101 plus our 273. So that gives us a value of 374 Kelvin, and our T1, which was the 15 degrees Celsius, that gives us a value of 288 Kelvin. So we just want to plug those values into the expression above, and like I said, be consistent with K2 and T2 and K1 and T1. So we have our ratio, we got our R value, we have our temperatures, and so we just want to be, somewhat slow and stepwise. If we take the natural log of that ratio, we get 8.098. If we take the difference of those reciprocal temperatures, we get 7.984 times 10 to the negative fourth. That would be a negative sign out in front of that. And so now we just need to, do some mathematics, right? We need to divide over. Obviously, the negative signs cancel out. So we would have our, 8.098 times our 8.314 joules per mole Kelvin, divided by our 7.984 times 10 to negative fourth, that's Kelvin to the minus 1. And that is equal to our activation energy. And so our activation energy here is equal to 84,326 joules per mole. Or looking at our values above, we could say maybe roughly 3 sig figs, or just say 84.3 kilojoules per mole. I suppose with the 15 degrees you might say 2, but I'm not too concerned about sig figs here, just the actual calculation. So there's our calculation of activation energy. So that's the deal with activation energy. Like I said earlier, we're going to now apply that to mechanisms and reaction order.